Okay, so there are just a couple more exams I still need to get back to folks, but I gave a few more back this morning. And so if there are questions about that, just let me know, like on a Friday or sometime if you want to talk. Looked like there were a few people that were missing a few of the cross-tab questions, but they weren't missing all of them. So it seems like no one got them consistently all wrong. A lot of people were getting consistently all right, which is good. There were a couple 100s in there. Yeah, just overall pretty good. There's a couple more exams I still need to give back, but if there are questions about your exam, those that you missed, just ask me and we can go over it. Or you might go back and look to see what you did and realize the mistake you made. But overall, pretty good. Yeah. So that's, those will be coming back. Those of you who haven't got yours back, you'll get those back just after this class here, a few minutes afterwards. Where we're at right now in the class, we did start with simple linear regression. Our next exam, the third exam will be coming up here. I'll be posting it this week. That will have on it correlation and simple linear regression. And so those will be the two things that will be on the exam that'll be posting probably either tomorrow or by Wednesday. So you will have time to take a look at that. So that will be up this week. That is the third exam. So will the homeworks. They'll be coming back for the simple linear regression. There will be one more homework for well, actually, no. Well, that's it. We'll for the first exam, we're not going to do anything else that will be on that. I'm sorry, for that third exam. There's nothing else that we're doing right now that goes on that third exam. So it's just going to be simple linear regression, and it's going to be correlation. And so that is what your third exam will be on. What we're going to do right now, though, is we're going to talk about the next step, which is called multiple regression. Okay, so you went over correlation already, and so that is looking at the relationship between two variables. So they're called bivariate correlations. And we noted how those can be positive or negative. They can range from -1 to +1, and they also have a statistical significance related to them. And then we started talking about something called simple linear regression. And so that is like taking a correlation and breaking it down further and seeing, okay, for every unit increase or every time I go up a level in this independent predictor X, how much does Y change? And so that's the kind of more fine-grained precision that you can get with simple linear regression, is that you're taking one variable and looking at its impact on another by the unit impact interpretation that we're using. So for every unit increase, what is the impact on the dependent variable? Okay, and we also, we did a couple exercises looking at simple linear regression. What I want to share with you right now is the PowerPoint on multiple regression. Now, multiple regression in this book, at least my version of this book, this SPSS book, it goes over the steps for multiple regression in chapter 16. And so that is something that you probably want to get to. You can take a look at what is in there. Follows right after the chapter on simple linear regression. But that's what we're getting into right now. And there is in addition to the PowerPoint, there's a PDF again on Moodle. It's very short. It's on multiple regression. Just take a look at that, read it. It's like 3 pages. And it has in it, I think, the data that we're going to use for today's example of multiple regression. And so, all right, so let me go ahead and get started here with multiple regression and why we use it. So there's lots of different types of regression. We're going to start off with the multiple regression that's an extension of the kind of regression we already did, which is called ordinary least squares. That's the estimation technique. You're trying to graph a line that minimizes the differences between the points on the graph. And so that's why it's called ordinary least squares. You're trying to draw that line that minimizes the points. Well, when you have multiple predictors, it gets more complicated than a simple linear regression. The math does especially. So at this point, this would be where we would, we could have done all this stuff by hand up at this point. But when we get to multiple regression, this gets into matrix algebra and stuff that really you want to use a computer for. But anyway, when you have multiple regression, you don't just have one predictor. You have multiple predictors, because we know that if you're studying something as complicated as, let's say, delinquent or criminal behavior, it's not just one thing that causes it. We know that there are lots of inputs into something that causes antisocial behavior. And so it's the idea that you can have really an infinite number of predictors in multiple regression, all estimating the impact that they have on y, some dependent variable. And so, just what do you mean by predictors? Well, these are just independent variables that are theoretically linked with an outcome, juvenile delinquency. So gender, age, social bonds. Theoretically here, all of these things would statistically be contributing to the likelihood of committing a delinquent act. And so what we need is some sort of mathematical ability to weigh just how much gender, age, and social bonds are contributing to the outcome juvenile delinquency, and how they compare with one another. What is more important, the degree to which you are bonded to society, or whether or not you're male or female? Male seems to be a pretty big risk factor. Being male seems to be a pretty risk factor for delinquency. But how does that compare to some other factors? That's the kind of thing that multiple regression can answer. So there is an idea, at least theoretically, that if you have a bunch of predictors and they're all mutually uncorrelated, like all your predictors for delinquency are not correlated with one another, then theoretically the impact of each one would be no different than in a simple linear regression. But that's realistically not true. So the reason why we need multiple regression is that we know that, just take for instance the variables gender and social bonds. We know that that girls and women on average tend to be more likely to say that they like school, that they like going to church, that they like doing these things that make them a little less likely to be involved in delinquency. So gender and social bonds, they're correlated. And so because those two things are linked, the reason why girls may be a little bit better behaved when they're teenagers than boys is because of their stronger connection to these social bonds to conventional others. And so when that kind of thing is going on, you can say, well, which matters more? That's when you have to have multiple regression, because looking at these things one at a time is not going to reveal to you what is the influence of one thing while adjusting for or accounting for the influence of another. Okay, and so this is the idea of controlling for the influence of some other variable. So you'll hear that term a lot in statistics when you get into multiple regression. The idea is that we want to look at the impact of gender independent of all these other things that we know have an impact on delinquency. So like age and social bonds. And so what is happening in multiple regression is it's saying, okay, well, what I'm going to do then is make matched comparison groups. I'm going to say, okay, if you want to know the impact of being male or female on delinquency, then I am going to create groupings where everybody has the same age, everybody has the same score on the social bonding measures, and then we'll see if all else being equal, gender still makes a difference. That's what multiple regression is doing. It's saying, okay, all else being equal, that means the same thing as controlling for. All else being equal, are males really more delinquent still, even after accounting for things like social bonds and maybe delinquent peers or something? Are boys really still more delinquent? And it turns out, yes, they are. So it shows you that even over and above the influence of other things that we know, at least theoretically, should have an impact on some outcome, that we can see what that isolated statistical effect is after we've accounted for or controlled for everything else. So we can say, make statements like all else being equal, this is the effect of, or controlling for variables 2, 3, and 4, here's the effect of variable 1 on my dependent variable. Okay, so that is conceptually what we're doing with multiple regression. So you can see why it's kind of indispensable when we're looking at behaviors, when we're looking at social attitudes, anything in the social behavioral sciences, you're going to need multiple predictors. And so this Venn diagram is showing that you might have two predictors, X1 and X2, both contributing to the outcome Y. And so you're going to have an independent contribution of X1 and X2, which is in the areas A and B on the Y circle. So that's going to be the independent influence that they have. But there's also going to be a correlation between X1 and X2 itself, and that's the shaded area D. And then there's going to be an area where all three of these things overlap, and that's that dark area C. And so what you're looking at when you look at the impact of something in a multiple regression, you're looking at that area C, where you're seeing the weight of one variable and the other variable, their independent influence, as well as the combined influence that they might have on top of their independent influence. And so you get this overlapping Venn diagram of how much one thing is a part of or explaining something else. And so yeah, in multiple regression, there's an assumption that independent variables may actually be correlated with one another, and for that reason, we have to control for their statistical influence in any model of behavior. And so when we're talking about regression, that's when we get into this language when people start talking about regression models. So people talk about modeling behavior. Well, in statistics, they're talking about having a regression equation that has lots and lots of predictors in it. And and then you can see if it's a linear prediction or nonlinear. So when we have multiple predictors, we're not talking about, if we graph this thing, we're talking about a two-dimensional image. We're talking about a three-dimensional image and not a line anymore. We're talking about a plane. And so what is happening, and this we can visualize because it's 3 dimensions. It gets beyond that, then it kind of gets really hard to show, if not impossible to show. But we can do it in 3 dimensions. The line becomes a plane, and now the plane, what the estimation technique is trying to do when you have multiple regression is trying to minimize the distance between those dots along the plane. And so it's trying to get that plane so it's sitting so that there are the least square differences between those dots, the actual observed data points. And so the plane is the hypothetical, that's the estimation, that's what we think is really going on in the population. And then we got the messy data of life that somebody has gone out and collected. And again, this is always an estimate. We're saying, okay, we think the data are an estimate. The more data we get, the more refined the estimate is. But we can get better and better at fitting this plane in those dots if we get more and more observations in there to see exactly how that plane should be estimated. And that's where mathematically where all your numbers are coming from in your multiple regression. It's trying to minimize the square differences between these dots by using a plane rather than a line. And we're still in the realm of linear regression. So we're still assuming that for every level or unit increase in X, Y goes up no matter where you're at on the scale of X. So the plane doesn't have curves to it. It's not curvilinear, it doesn't bend. There's examples in the book. It talks about nonlinear effects, but we're not there yet. I don't know if we're going to get there in this class, but yeah, we're assuming it's just linear, that everything kind of proceeds on. It can be modeled in a straight plane or a straight line. Okay, and so there is reasons that we further theoretical reasons why we want to do multiple regression. It is possible that what you have going on, let's say between grades and delinquency, grades represented here with X1 and delinquency is Y, that you would notice that there is a negative correlation between delinquency and grades. That is that the kids that do really well in school tend to be less delinquent, while the kids that are highly delinquent don't do too well in school. Well, some might argue that that is not really showing causation. What is being shown here is just mere correlation. And what is really happening is if we looked at a third variable, we found a third variable called, let's say it's called self-control, and that we noticed that people who have really high self-control scores also tend to have low delinquency scores, really high grades. And so it may just be spurious. That is, the relationship between grades and delinquency may be spurious. There may not be a real statistical relationship there. We would figure this out. We would be able to know this if we would have a measure of self-control. If we had a multiple regression and we also controlled for self-control, the effect of grades in the model would go away. The statistical, the significant effect of grades in the model, in the regression equation, this line would go away, and we would notice that really what's going on is that it's self-control that's predicting the ability for people to get decent grades, and it's also predicting people's ability to not get in trouble. And so you can test for spuriousness type effects where people might think maybe naively or just kind of pedestrian way of thinking that it's really, kids' grades are what determines how delinquent they are. They get bad grades, they feel bad about themselves, and they act out. Well, it may be that, or it could be some alternative hypothesis where you really think it's this psychological tendency, this underpinning of being really impulsive that's doing it. Well, you can answer those kind of complicated questions with multiple regression. There's also something called mediation that you can look at in multiple regression. This is this idea that, well, it may be that one thing is related to another thing because of some third thing. So we know that there is a relationship between family structure and delinquency, that the tendency is kids that come from intact married families, two-parent families, tend to be less delinquent on average than kids that come from especially divorced or separated families. And so, well, what's going on there? Well, it may be the case that kids that come from intact families, there is something going on in the family that we call family process, that there's the kind of bonds in those intact families are more secure because the family is intact, and maybe because of that family process, the more secure bonds with mom and dad. That's why the delinquency is lower in intact families as compared to families that are separated or divorced. And so that's another thing that you can figure out with multiple regression. You could say, okay, well, we have noted what the impact of family structure is on delinquency, but we also have what's called these family process measures. And so you could do this with AdHealth. In fact, there's a link here to an article where people looked at the AdHealth data and asked the question, well, is it family process that explains the effect of family structure on delinquency? And what they found is, yeah, that's the case, is that once you start accounting for things like how emotionally attached you feel to mom and dad, how involved they are in your life, just if it looks like it's a warm, loving family, then that explains away much of the family structure effect. That is, once you account for family process in the regression equation, the statistically significant effect of family structure starts to go away. And so that means that really the reason why the two-parent family seems to be doing better is that the family process variables are working well for those kids, and so that's what explains it. But again, these are one of these things that you can get into with multiple regression. You can answer these kind of these more complicated type questions. So yes, issues of spuriousness, issues of mediation are things that can be addressed with multiple regression, that you just you have one variable that's related to something else and you think, I think there's something else going on here, and then you put that in the equation, and the thing that you originally thought was important, like whether or not you came from an intact family, doesn't seem to matter as much once you account for family process. So that's called a mediation effect. Another thing that's really useful, and we'll see this in the printout in SPSS, is that in addition to the unstandardized betas that we use in our regression equation to find out the predicted value for something, there are something called the unstandardized beta, or the standardized beta. So we use the unstandardized betas in our regression equation. That's what we did in the homework. The standardized betas are like correlation coefficients. They're standardized in a sense that you can make apples to apples comparisons between the variables in the model. So you can, even if things are measured differently, so if gender is measured 0, 1, and another variable is measured 0 to 100, you can still make apples to apples comparisons and how much of an effect they have on the dependent variable by looking at the standardized beta estimates. Because they're on a standardized scale, they have been transformed into a z-score, so to speak. So they're all on the same scale, and you can make those apples to apples comparisons, like what matters more, does gender or social bonds? Because by looking at the regular betas that we did already, you can't make that kind of statement because they might be in different scales. Okay. So that's standardized beta, which we'll take a look at. And just noting again, I'll say this a couple more times, the betas that we looked at already, the B in the equation for regression y equals a plus bx, that little b, baby b, that is the unstandardized beta. That's what we use for the equation. Big B, or the standardized beta, that is what we'll talk about today. And that usually is looked at in multiple regression when you want to know, okay, what has the stronger, what has more strength to it? What's, the effect sizes can be standardized, and you have to do that to make apples to apples comparisons. Okay, so here is some data that is in the PowerPoint slideshow. So what I'm going to do, I'm going to go ahead and I want to look at the effect of prior arrests and age on future arrests. And so I want to see what is the effect of prior arrests on future arrests, controlling for age. Likewise, what is the effect of age on future arrests, controlling for prior arrests? All right, so this is a multiple regression because we have two independent predictors. We have prior arrests and age. And so now we know these two things are two different variables. Your age is a separate thing, independent thing of prior arrests. You will age no matter how many times you get arrested. So it really is a different thing. But we also know those two things are correlated, right? There's something called the age crime curve, and risk of arrest goes up pretty rapidly in teenage years and descends pretty quickly thereafter. So there is a correlation between these two things. And for that reason, age is something you often account for when you're looking at arrest data. If you want to know the effect of, let's say, something else like the percentage of single parent homes in a community, or so, you want to look at the age structure of the community as well. You got a lot of young boys, it's going to be high no matter what your family structure is like. Okay, so let me, I'm going to cut and paste from here. So we have prior arrests, age, and future arrests. Copy. Let me, just a moment here, folks. I think I need to, I'm going to try and pasting this on a new page because that sometimes works. I'm just pasting this data onto a new page. Oops. In Word. Okay, let me go back, and now I want to, let's see. Let me go into my SPSS. Okay. Let me, I'm going to open up a new data sheet. And I'm going to go ahead and go on data view. And I'm just going to paste this in here. Hopefully this will paste. Good. Okay, so we have that pasted in there. Okay, so we have then, I don't want to go ahead and put labels on these so I know, or at least name them. So I just keep it straight in my head what I'm looking at here. And so, yeah, so we have a prior arrest, age, and future arrests. Okay, so I'm gonna go ahead and go in here and I'm gonna name these. If for some reason my screen doesn't show, just let me know, because I did switch to variable view, folks. I'm on variable view and I'm just naming these so I can remember what I'm doing. Prior arrest, and this is age, and then the third one was future arrest.
I think it froze.
Okay, let me, okay, thanks for saying that. Let me go back to what I was doing. Okay, so can you see this now? I'm on variable view, and what I did was I just put names in for the 3 variables. Can people see that? Yeah, so yeah, I just cut and paste directly from the PowerPoint, put it right in there, and then I went ahead and put names in here for these variables, just so we have some labels when we look at the data, so we're not looking at just generic names for the variables. Okay, so we got prior arrest, age, and future arrest. All right, and so what we want to do here is we want to go up to where it says analyze, and we want to go to where it says regression, and we're going to the same spot. We're going to where it says linear regression, okay? And once we're in linear regression, we have this same setup here. We can go, we can put our prior arrest in here as an independent variable. We can also put age in there as an independent variable. And we're going to put future arrest in there as a dependent variable. Right. Okay. So the big difference here from last time is now we have 2 independent variables in the independent variable box. And so both age and prior arrest are going to be estimated in their impact on future arrest. Okay. So when we go ahead and do this, let me stop sharing this and go back to my other screen, because I've got a feeling that this is, well, I know it's probably stopped. Okay, so you should then be able to see where it says regression variables entered. So we got 2 variables entered then, age and prior arrest. And we have some output here. Let me, before I get down to the standardized betas, which I want to make sure and point this out to you today, let's go back to this model summary thing. Now recall what the R square is. So the R square, that's called the coefficient of determination, or the amount of variation that is explained in the dependent variable by the independent variables. Okay, so you have a data set here with people that vary in how many times they've been arrested at time 2, future arrests. Well, what explains why some people have more arrests than others? Does the number of prior arrests explain it? Does age explain it? Yeah, they both explain some of it. The R square, when we have multiple regression, what we want to look at is what's called the adjusted R square. We want to look at the next one over, because R square will go up just by putting extra variables in the regression equation. It'll go up even if they don't really add too much to explain the variation. Like it'll go up even if the predictors themselves are non-significant. Because of that reason, when we're doing multiple regression, we want to look at the adjusted R square. Notice it's a little bit lower. So the adjusted R square is the one that you want to look at when you're doing multiple regression, when you have more than one predictor here. So we have prior arrest and age predicting future arrests. And so that adjusted R square is the one you want to look at. So that's saying that the 2 predictors, prior arrest and age, account for about 67% of the variation in future arrests. So prior arrest and age account for about 67% of the variation in future arrests. So if the R square and the adjusted R square is a proportion of the variation that is explained. And so it can't get higher than 1. And so that means you can interpret it as a percentage. And so that means a 0.67 is about 67% of the variation in the dependent variable. Future arrests can be explained by these two independent predictors. Okay, so that's really good, right? You know, so you're explaining a lot of why people are at high or low risks for arrests in the future just by knowing what the rap sheet is, how many priors they have, and then also it turns out their age. Okay. So when we come down here, we go to we see this ANOVA. Okay, so we're going to talk about this again when we get a little bit further into multiple regression. But what the ANOVA test is doing, it's testing for overall differences in the dependent variables average according to differences in where you're at in the independent variables. And so it's very much like the ANOVA. It's looking at variations within groups compared to the variations between groups. And so it's not as if everybody of the same age has the same number of future arrests. There's variation, right, within groups. But then there's variation between. You get older people are less likely to be arrested than younger people. And so it does that comparison for the entire model, for everything in there. It has this whole big equation where you're putting all the variation within compared to the variation between, and it's giving us this F test. And this F test tells us if any of the independent variables in the model are significant at all, if any of them are moving the needle at all for the dependent variable. That is, if the average of the dependent variable is different at all if you're high or low on one of the variables, on any of them. So it's an overall global test, kind of like what the chi-square is test for crosstabs, what the F is for ANOVA. This F here for this ANOVA, for this regression, is just telling you if there are any significant effects of the independent variables on the dependent variables, any at all. And it's saying, yes, there are. This is a significance test. The alpha value is 0.009, so that's less than 0.05. And so you would conclude that, yes, the F is statistically significant. There are differences in average future arrests according to your rankings on these independent variables. Okay, so that's the F. And so that, again, tells you if there's any significant effects whatsoever. There can be situations where you don't see significant effects in the model, but the F is significant. And that just may be a coding issue that we can get into that later. But okay, well, that's the F for when you're running your multiple regression. Down here, here is our regression for priors and age predicting future arrests. Okay, so what we notice here, this is our unstandardized betas. So this, for every additional prior arrests, future arrests go up by 0.519, so about a half arrest. For every additional age, every additional year in age, arrests go down by about a quarter, or 1/5, about 0.221 arrests. So the more priors you have, the more likely it is that you're going to have a high number of future arrests. The older you are, though, the less likely it is that you're going to have a high number of future arrests. Okay, and so that is the unstandardized, and then so it would be the equation here would be y equals, here's A, so here's your intercept, 9.642 arrests, and then you add to that your first B, this is plus 0.519 times x1, whatever you want to put in for how many number priors, and then plus a negative, you just go plus a negative second B, negative 0.221 times x, time whatever, and then you plug in an age for that. And that's going to give you the estimated number of future arrests for somebody with a given number of priors and a given age. So you can do that with that equation. You can get the predicted number of future arrests for somebody has 7 priors and is 42 years of age or something like that. You could figure that out. Okay, well, that's unstandardized betas, and that's how you figure out the equation. This over here, standardized coefficients beta. Okay, so these are the standardized betas. These are on a standardized scale, meaning you can make apples to apples comparisons between two variables that are measured in wildly different scales. Like I said, one could be measuring 0 to 1, other could be measured 0 to 100. You couldn't do that in the unstandardized, but the standardized you can. You can say which has the strongest effect in absolute terms. Which has the strongest effect in absolute terms? Okay, so you forget about the negatives, more positive. Which number is biggest in absolute terms? Prior arrest, 0.565. Age, 0.517. Well, they're close. They both have a very similar effect size. The strength of the effect is similar, but a prior arrest is a little bit stronger. Again, you forget about the negatives or where that's positive. In absolute terms, what's the bigger number? What has the biggest effect? This has a pretty strong negative effect, but this has a relatively stronger positive effect. So what has a stronger effect? Prior arrests do, even though age still has a strong effect. Okay, are these things statistically significant? And we've looked at this already, that prior arrest and age are both statistically significant. So betas are on a t-distribution, so you look at a t-test to figure this out. But the t here is shown as 2.844, and the significance, the alpha value here is 0.025, and so that's significant. So that's less than 0.05, so that's significant. And then here we have a negative 0.2602, and then we have a significance level or an alpha value here of 0.035, and so that's also less than 0.05. And so both of these have a statistically significant impact on estimated future arrests. And remember, significance is different than effect size. Here we're looking at effect size. You can look at it in terms of the unstandardized coefficients. And then if you want to make apples to apples comparison, you can look at the standardized coefficients. But that's different than significance, because they can, something can have a big effect size but not be significant. That's just usually because you have too small of a data set to detect it. You're committing a type 2 error. But in this case, both are significant, okay? And so that is what we're doing here with multiple regression, okay? We are able to put in multiple predictors. We can take a look at what the estimated future number of arrests would be for somebody with a certain number of priors, a certain age. And as you can imagine, this thing can continue on so long as we have variables and values for those variables, for different variables like their gender, whatever you can think of. This equation could keep going on and on, but we can use these two variables here to make a more informed estimate as to what the future arrests will look like than just using one variable. And so both of them are providing us useful information about future arrests. And so that I think is all I want to get to right now. I'm going to have another assignment, a homework assignment posted here that we can work on Wednesday. But I think that is about all for today. Are there any questions about what we looked over? You want to be looking over chapter 16, that PDF. But I think I want to stop there, and we'll get into another, we'll do a homework together on Wednesday. I'll have that posted before Wednesday. And then you can take a look at that, and that's what we'll do Wednesday though, is a multiple regression type homework, okay? All right, folks. So if you have questions, you want to hang out and talk for a little bit about this stuff, that would be fine. If not, you are free to go. And a couple more people I need to give tests back to, but that should be coming back shortly.